I hope I'm audible. So welcome back to week 10 of the problem solving session for the thermodynamics course, and in this week again we will be continuing with the concepts of entropy, and we will solve some problems related to and entropy generation. We will see what entropy generation means, and we will also look upon the principle of increase of entropy. So this is the content for this week's session, and as per our regular agenda, I'll go through the topics that were discussed by Professor Anand in the lectures. I'll briefly go through them. Again, I will not dive deep into each and every derivation and statement. That is being thoroughly done by Professor Anand in his lecture. So if you have any doubt, you can go back to the videos uploaded in the course website, and then you can rectify your doubts. But again, in between also, if during the to this session, if you have any doubt, you can always stop me and clarify it. I'll try my best to do so. But if you're still having some doubts regarding the topics, you can go back to the videos by Professor Anand and clarify it, or you can put your doubts in the discussion forum. Okay, so we will wait for 2 more minutes. Let's see if other students join. Otherwise, we will start the session. Okay. So so okay, I think we can start. So okay. So last week we were discussing about the thermodynamic property, that is entropy. We found out that, like internal energy, entropy is also a thermodynamic property, or it's a point function or a property of a system. Like, all these terms can be chosen interchangeably to define it. So yes, so we found out that entropy is also one of the thermodynamic property, right? And it's a point function, so it depends on the end points of the process, right? And since it is a thermodynamic property, just one second. Since it is a thermodynamic property, so the cyclic integral of this of entropy is the cyclic integral of the net and the cyclic integral of the net entropy change would be 0, because this is thermodynamic property, right? So we found out that entropy was defined as the net heat transferred, the ratio of the net heat transferred over the temperature at which the heat was transferred, right? So we found out that Ts, or change in entropy, can be defined as delta Q reversible by T, and this equation holds valid only for a reversible process. Okay, so if if this is irreversible, then this equality does not hold true, and we will see what happens to this sign in the later part of today's discussion. Okay, so now if the process is reversible, because first of all this is defined only for a reversible process, right? So the reversibility of the process has to be considered. So if the process is reversible, and now if I say that if the process is adiabatic as well, it is the net heat transfer during the process is 0, then the net change in the entropy would be 0, and that's why an isentropic process or a constant entropy process can also be taken as a reversible adiabatic process, or basically a reversible adiabatic process is an isentropic process. Okay, now we look into the different the slopes of the different processes in a TS diagram. So in the previous session we briefly introduced the TS diagram, the TS plot and its uses. We have till now we have seen different types of plots. If I recall, we have seen primarily the PV plot, the TV plot, and even the PT plot during the phase diagrams, right? So here we will see the TS plot, and we'll see the slope of the different processes. There's a constant pressure or a constant volume process, or the different types of processes that can be portrayed in a TS plot. Okay, so as you can intuitively understand that for a constant entropy process, the it can be noted as a vertical line in the TS plot, right? So this line shows a constant entropy process, which basically means that the entropy does not change with the change in temperature. Okay, or there is no change in the entropy. Similarly, for a constant temperature process, where for T equals C, it can be represented by a horizontal line in the TS plot. Okay, now now if you go back to the PV diagram, the constant temperature curve is actually a rectangular hyperbola, if you recall, right? In a PV diagram, the constant temperature line is a rectangular hyperbola. For more reference, you can go back to the lectures by Professor Anand, and even the problem solving sessions we were discussing why it is rectangular hyperbola, so I'm not going to repeat that. It's basically the xy equal to c equation, and this basically implies a rectangular hyperbola in a xy plot, right? Similarly, that's why PV equal to c would imply a rectangular hyperbola in the PV plot, and PV equal to c is a governing equation for an isothermal process, right? It basically comes out from the ideal gas law. If PV is equal to mRT, R is a constant, M is a constant. If T is also a constant, then PV will be equal to some constant C, then it will represent a rectangular hyperbola in the PV diagram. Similarly, PV gamma equal to constant is an adiabatic is a governing equation for an adiabatic process, and this process would tend to have a higher slope, shown by this line, in the PV diagram. Similarly, for a constant pressure process, it can be represented by a horizontal line in the PV diagram, represented by this blue line. And finally, a constant volume process, for V equal to C, it will be represented by a vertical line in the PV diagram, right? Represented, shown by this red line. Okay. Now, if we want to represent a constant pressure and a constant volume process in a TS diagram, so let us start with a constant pressure process. Both are shown already, but let me start with a constant pressure process. So it can be shown as a curve in the TS diagram, and similarly the constant volume process can also be shown as a increasing curve in the TS diagram. Okay, now if now what we are concerned is that which among these, how to distinguish between these two processes, that P equals C and V equals C. Now how they are different with each other, or like if two processes are consecutively shown, simultaneously shown in the TS diagram, which of the two processes will have a higher slope? So that basically we are trying to distinguish between these two in a TS diagram, right? How to distinguish a constant pressure and a constant volume process in a TS plot, right? So that is what our primary concern is. So in order to do that, we take the help of the thermodynamic property relations, right? So for an ideal gas, we know that TdS is equal to du plus PdV. It's one of the thermodynamic property relations or the Gibbs equation. Now for a constant volume process, we'll see that dV would be equal to 0, then the TdS would become equal to du. TdS would be equal to du. Now ds, du can be written as Cv into dt for ideal gas, and similarly we can TdS would be equal to Cv into dt. Now if we take ds in the denominator and Cv in the denominator in the left hand side, we will get dt by ds is equal to T by Cv, and you will realize that for TS diagram, dt by ds primarily denotes the slope of the line. Okay, so the slope of a constant volume line would be given by T by Cv. Okay, which is a function of temperature and the specific heat for a constant volume Cv. Okay, so now if we look similarly, let us keep this here. Now if we similarly look for a constant pressure process, again we need to take the help of another thermodynamic property relation, that is TdS is equal to dH minus VdP. Why we are taking dH? Because now we want to see a constant pressure process, right? So for a constant pressure process, the enthalpy comes out to be a more understandable choice, because it's a function of the specific heat at constant pressure Cp into dt. So enthalpy turns out to be more reasonable thermodynamic property in the case of a constant pressure process. And you might have seen this time and time again in the different types of formulas or derivations that we have used, that for a constant pressure process, enthalpy comes out to be the primary quantity of concern, right? So similarly, for a constant pressure process here, we will take TdS equal to dH minus VdP. Basically, we take the TdS relation, which has an enthalpy in the case of a constant pressure process. Why? Because you will see that the terms become much more simpler. TdS would become equal to dH minus VdP, and for a constant pressure process, dP would be equal to 0. So the second term will go out, right? So we will be left with TdS is equal to dH. Again, dH can be written as Cp into dt, or TdS is equal to Cp into dt. Then dt by ds would give us T by Cp. Now we know that for a ideal gas, Cp is greater than Cv. If that's the case, then dt by ds, sorry, let me write it here, something like that. If Cp is greater than Cv, right, then dt by ds for P equal to C would be less than dt by ds for V equal to C, right? And that's why a constant volume process has a higher slope than a constant pressure process in a TS diagram. Okay, so that's the conclusion that we get. So if we want to denote a constant volume process, it must have a higher slope compared to a constant pressure process that has been shown simultaneously in the TS diagram. Okay, so we will see that these kinds of plots comes into picture when we are considering the diesel cycle. So diesel cycle constitutes both a constant pressure and a constant volume process, right? So we want to know how to distinguish these two plots, right? Which of the two plots would have a higher slope? So we can do it by if we know if from this direction, you can easily tell that a constant volume process would have a higher slope compared to a constant pressure process in a TS diagram. Okay, only for a TS diagram. Okay, now if you are going to show the similar thing in a different kind of plot, say a TV plot or a PT plot, then the equations will change accordingly and the slopes will behave accordingly. Okay, so just 1 second, just kindly wait for 1 second. I have something just 1 second. I have just one concern that I'm trying to clarify. Okay. So I am sorry. I was saying that the diesel cycle has both a constant volume and a constant pressure process. It does not turn out that it is not the case. So diesel cycle only constitutes just 1 second. Maybe sorry for the confusion. Okay, I don't want to give false information, but that's why I'm just revisiting it again and again so that it becomes clear. Okay. Yeah. So actually, I was correct initially that diesel cycle does indeed have a constant volume as well as a constant pressure process. So while you are drawing the plots, in order to be correct, if you want to represent the diesel cycle in the TS diagram, you need to rightly plot the constant pressure and the constant volume process in the case of a diesel cycle. Okay, so I was right initially. I was getting a bit confused with the dual cycle and its because both processes are continuously shown one after another in the case of dual cycle. I was getting a bit confused, but sorry for that. But it's true, it's correct that for diesel cycle both a constant volume and a constant pressure process comes into picture. So that's why if you're going to study these air standard cycles or even IC engines, while plotting the constant pressure and the constant volume processes for a diesel cycle or any kind of air standard cycles or even vapor power cycles, if at all it constitutes both a constant pressure and constant volume process, and if you're going to analyze it through the TS diagrams, it's good. It would be very ideal if you know the slopes of or how the slopes of the constant volume process and a constant pressure process varies in the TS diagram. Okay, so that's what this is what we wanted to show. Now let us take an example of a turbine. Okay. Before that, I would suggest I should primarily first of all discuss the entropy, the process of increase, the principle of increase of entropy. Okay, so I have a statement written here that is entropy increases in an irreversible process. Okay, so that's a statement that I want to prove, or I must say, Professor Anand proved in the class, so I will just reiterate it again. I will go through the derivation once and hope it is clear. If you have any doubt, you can ask me. I will try to sort it out for you. But otherwise, just go through. Let us just go through derivation once. Okay. So consider this diagram. This is a TS plot showing a thermodynamic process. So basically, it denotes a thermodynamic cycle from between points 1 and 2. So parts A and B constitute a reversible cycle because both part A and part B are reversible parts, but part C is an irreversible part. Okay, so if we go from 1A to B1, it constitutes a reversible cycle, but if we consider the part 1A to C1, it constitutes an irreversible cycle because part part 2C1 is an irreversible path. Okay. Now from the Clausius inequality, we know that the cyclic integral of delta Q by T is less than or equal to 0. Okay, and it is equal to 0 in the case of reversible process and less than 0 in the case of irreversible processes. We saw that in the previous week's discussion. Okay, now for the for the reversible cycle 1A to B1, we will have that the net change in entropy is 0 because for a cyclic process ds for a cyclic process the cyclic integral of a thermodynamic property would be equal to 0, and since entropy is a thermodynamic property, so delta S would be, sorry, ds would be equal to 0. So we will have that the cyclic integral of delta Q by T would be equal to 0, because this primarily is equal to ds in the case of reversible cycle. So we will have that delta QA by TA plus the integral of delta QA by TA from 1 to 2, and the integral of delta QB by TB from 2 to 1 is equal to 0. Okay, this sum is equal to 0. This is for a reversible cycle. Now if you consider irreversible cycle, we have that from 1A to C1, we can represent it as the integral from 1 to 2 for the integral of del QA by TA from 1 to 2 plus integral of del QC by TC from 2 to 1. And this would be less than 0, because we know that the cyclic integral of delta Q by T is less than 0 in the case of an irreversible cycle, right? But we know that whether it be a reversible or an irreversible cycle, it doesn't matter in the case of a thermodynamic property. So the cyclic integral of thermodynamic property, rather the path achieved the path used to achieve this cycle was reversible or irreversible, the change in the thermodynamic property won't matter on the path that was chosen to achieve that change in the property, right? So the so ds would still be 0 in the case of a cyclic integral, in the case of a irreversible cycle. Okay, but we know that the cyclic integral of delta Q by T, this entity, is less than 0 in the case of an irreversible cycle. And because delta S is equal to 0 and this entity, cyclic integral of delta Q by T, is less than 0, then it basically implies that cyclic integral of del Q by T is less than ds in the case of a irreversible cycle. So basically it would imply that the integral of delta QA by TA from 1 to 2 and the integral of delta QC by TC from 2 to 1 should be less than 0 in the case of an irreversible, or basically it should be less than ds. Why? Because ds is equal to 0, right? So we have that ds is greater than delta Q by T, and if not mentioned explicitly, it meant delta Q by T means that delta Q by T for an irreversible cycle. Okay. Yes. So delta S again can be denoted as S2 minus S1, like from one side, from point 1 to change in the entropy from point 1 to 2. It should be greater than the integral of delta Q by T from 1 to 2. Okay. So so we have that ds is greater than delta Q reversible by T. Like here now we have explicitly mentioned that it's for a reversible process, and delta, so in general we will have delta S is greater than equal to delta Q by T, and it will equal in the case of a reversible process only. Okay, and that's how we distinguish between a reversible and irreversible process. So for a reversible process we will have ds is equal to delta Q by T, and we will say represent it as reversible, and for irreversible process we will have delta S is greater than delta Q irreversible by T. Okay, so in general we can write like this, ds is greater than equal to delta Q by T. So similarly for cyclic integral we will have the change in the entropy S2 minus S1 is greater than or equal to cyclic integral of delta Q by T. Okay, so so now if we consider insulated system, okay, insulated system would have the net change in the heat flux, or the net change in the heat in the net exchange of heat is equal to 0. Similarly, if it's of course if it's an insulated system, it has to be a closed system, so the net mass transfer will also be equal to 0. In that case, since Q is equal to 0, we will have change in the entropy is greater than or equal to 0, right? Because since we do not know whether this heat interaction that we are considering in the case of a insulated system, whether this system, all the processes within the system are reversible or irreversible or not, we do not know it explicitly. So we will just write that the net change in the entropy for an insulated system would be greater than or equal to 0, because delta Q is 0 as it is an insulated system, right? There is no increase in the entropy because of the heat transfer. There can be increase in entropy. Why it is a greater than equal to sign? Because there can be change increase in entropy because of the internal irreversibilities within the insulated system. Okay, so that's why if we consider insulated system, uh, we will have the net change in entropy ds as greater than or equal to 0. And if we consider the net heat and work interactions and even the mass transfer equal to 0, which basically implies an isolated system. It implies that for an isolated system we will have that delta S or ds is greater than or equal to 0. And as our universe can be considered as an isolated system, because if we consider the entire universe, right, if we consider the entire universe as a closed isolated system, and all the processes starting from the burning of fire on earth to the burning of hydrogen in sun to create the luminescence that is that creates light that creates the light from the for the sun, or all the galaxies or all the black holes that interact that are existing in the universe. If we consider all these processes in the universe as the processes within the universe and constitute the universe as an isolated system, then and if we consider all these processes that are occurring in the universe as a singular system, then this entire universe can be considered as an isolated system, right? And that's why if we find the analogy, then we can write that for the universe we will have delta s ds s greater than or equal to 0. I'm sorry that I'm confusing with s and ds and delta s. So delta we usually use for we usually use for part functions, and since entropy is a point function, we will use ds. Okay, sorry for that. So for universe we will have that for the universe we will have that ds is greater than or equal to 0, and this is known as the principle of increase of entropy. Okay, and this principle of increase of entropy is the direct consequence of the second law of thermodynamics. Okay, like it's right now there might be some little bit of confusion, like how we can directly say that. But if you try to correlate everything that we have studied till now, all the examples, the Kelvin Planck statement, the Clausius statement, the Carnot engine that we have studied, the Carnot's theorem that we have discussed, all this, like if you try to compare, and even this, the principle of increase of entropy, if you try to compare all these statements and try to find a correlation, you will see that this statement, the principle of increase of entropy, is the direct consequence of the second law of thermodynamics. And sometimes in some books or in some references, even this statement is known as the principle of is known as the second law of thermodynamics. And if it is correct, it's indeed correct, and because all these statements can be used interchangeably. But for the scope of this course, we have we have separately discussed all these statements. This is a Kelvin Planck statement, or the Clausius statement, or the Carnot's theorem. But all these theorems or statements just confine down to the same conclusion, that the entropy of the universe tend to increase. Okay, and there's of the universe. Okay, not the individual system within the universe. There can be reduction in the individual system within the universe. For example, if you use an AC, right? If you use an AC to cool down a room, then the entropy of the room would basically go down, because temperature goes down and there is a heat flux going. We can consider the heat, the net heat content in the room going down, right? So the entropy of the room would go down, but the energy required to run that AC, the working of that AC, or the energy required to put the to pump the heat out of the room, or I can say the energy interactions required to pump the heat out of the room will result in a higher entropy generation than when compared to the net reduction in the entropy within the room. So the net sum of the increase in the entropy because of the pumping out of the heat from the room would be greater than the net reduction in the entropy of the room because of the functioning of the air conditioning. Okay, so that's what basically we basically mean by the principle of increase of entropy. So it will basically imply that, like, we can dissociate the net entropy of the universe as delta S system plus delta S surrounding, and this will be equal to delta S universe. So delta S system would basically mean the system that is in our consideration. So in the case of AC, it will be the room that is being cooled down. Okay, so the room that is being cooled down can be considered as a system. So if you look into the only the room itself, the net entropy of the room will go down because the heat is being pumped out of the room, right? Now, but for pumping this, let me just write it. Okay, I think that will be much more clearer, just me saying it. So delta S system plus delta S surrounding would constitute the net change in the entropy of the universe. Okay, and by the definition of system itself, we know that system is anything that is in our focus, that we are focusing upon, right? So now if we are focusing upon the room that is being cooled down, then the entropy of the room would go down, right? Because heat is being pumped out of the room, and thus the room is being cooled down. Okay, but now if if we consider all the energy interactions that was involved in the working of the AC itself, right? And AC itself, and say all the electricity that was required to run the AC, and all the fuel that was being burned to create the electricity that was required to run the AC. If we consider all the entropy interactions in those cases, you will see that it will basically experience an increase in the net entropy of the surrounding. Okay, all these electrical wires, the coal that was burned to generate the electricity, all these things, all the entropy interactions that was required to generate the electricity to run the AC can be considered as entropy interactions of the surrounding, and you will see that this will result in a net increase of the entropy of the surrounding. And now if we add both this up, you will see that the net result would be a net increase in the entropy of the universe. Okay, so that's what we mean by the principle of increase of entropy. So if we consider a particular system, it's not necessary that it will always, the entropy will always increase. Of course, the entropy will go down, and that's why we're feeling the cooling effect, right? So entropy can go down, right, for a particular system, but net summation of the entropy change of the universe, it will go up, and that's what we basically mean by the principle of increase of entropy. Okay, so now we will look into the efficiencies, or how can we define the efficiencies of different thermodynamic systems, or thermodynamic you can say apparatus such as compressors, pumps, nozzles, and we'll see how the functioning of these thermodynamic systems can be defined, and how the irreversibilities, how the effect of irreversibilities are now taken into picture while analyzing these thermodynamic systems. Okay, so in the case of a compressor, let me just go back. I think, okay, we started with turbine. Sorry for that. Let us start with a turbine. Okay, let's go with the order of by which Professor Anand presented in his lectures. So let us start with turbine. Simple. So as we know, turbine is basically a thermodynamic system used to expand the hot vapor or steam and obtain the energy to rotate by rotating the shaft. Okay, they use those steam and vapor to rotate the turbines and produce energy. Okay, so and since there is an expansion, basically it will imply that the pressure of the steams will go down. Okay, steam or the vapor or any working fluid that is being considered will go down. Okay, so the pressure goes down from Pi to P. Pi is the pressure at the inlet and P is the pressure at the outlet. So pressure goes down. Okay, and we say that if we consider the net heat interaction as 0, and if we consider the process reversible, it will basically imply that this expansion process is a reversible adiabatic process. Okay, so for a reversible adiabatic case, again the net change in entropy would be equal to 0. Okay, so it will basically imply a straight vertical line in the TS diagram, okay, from pressure P1 to P2. Now from the first law we have that, or basically the steady flow energy equation, we have that d by dt is equal to q dot minus w dot plus mi dot h into hi plus vi square plus dzi minus m dot e into he plus ve square plus dzi. Okay, from, if we consider mass conservation, we, from for steady state we will have that mi equal to mi dot is equal to me dot, or let us consider mi dot equal to me dot equal to some generic m dot. Okay, now if we substitute mi dot and me dot as m dot, as I have shown here, and if we consider net heat interaction as 0, then we will have that. And moreover, if we consider net change in the kinetic and the potential energy as 0, because basically the net change in the enthalpy is much more greater than the net change in the kinetic and the potential energy. So if we consider that, we will have that the net work produced by the turbine is equal to hi minus he. Okay, for a reversible adiabatic case. Okay, or if we consider the point 2 or the stage 2 seconds, the stage 2 of the system, if we are considering a reversible adiabatic case, so we can consider ds as 0, so we can consider an isentropic case, so we can denote it as some point 2s, which represents the point that was achieved in the TS diagram after expanding the steam in a reversible adiabatic manner. Okay, so the net work done, the reversible work done would be h1 minus h2s. Okay, this is a reversible work done. Now if we consider an in reality, since there would be irreversibilities in the system because of friction in the turbine shaft, or the change in the temperatures, or because of the ineffective insulation. In that case, there might be some irreversibilities in the system, and let us say that the instead of achieving 0.2s, the steam has expanded from 1 to say point 2. Okay, this is denoted by the red line. The process is denoted by the red line, which basically denotes a reversible process. So, and point 2 is somewhere higher. Okay, so now you can clearly see that this h1 minus h2 would be lesser than h1 minus h2s. Okay, so or because point 2 is higher than is higher than 0.2s in the TS plot, so it would basically imply that the net work achieved during from an irreversible process is lesser than the net work achieved through a reversible process. And it is quite intuitive to take it that way, because of irreversibilities, the net work obtained was lesser than what we could have obtained in a reversible adiabatic case, okay, or an ideal case. And that's why the isentropic efficiencies in such case can be defined as the smaller work or the smaller work achieved from the ratio of the smaller work over the bigger work, or the higher amount of work achieved. Okay, because you will see why I am telling it you in such a manner. Okay, so in this case, the smaller work achieved is the net the actual work that is achieved from an irreversible case. Okay, so we will have that eta isentropic for an turbine would be W actual by W reversible, because the net work achieved in the actual case is lesser than the net work achieved during the reversible process. So we will have that eta isentropic as W actual minus over W reversible, or H1 minus H2 over H1 minus H2s. And if you want to represent it in terms of temperature, you can also represent it in terms of Cp minus T1 minus T2, or Cp into T1 minus T2s. Okay. Why I have not used Cp into T, because it's valid in the case of an ideal gas only. Okay, so that's why I am not using that, or any fluid in a constant pressure process. And since this is not a constant pressure process, because it is already told that it is being done, pressure is being increasing, so we cannot take that. Okay, but if it was ideal gas, then we could have considered. Okay, now now let us discuss about a compressor. It's just a reverse turbine. I'm just by saying that the turbine expands the working fluid, and similarly the compressor compresses the working fluid. Okay, so the pressure would go up. Compression would basically imply that the pressure would go up, right? So just kindly wait for 1 minute. So yes, so again we can consider similarly that pressure is now increasing from from P1 to P2, where P2 is greater than P1 in the case of a compressor, and reversible adiabatic case would be such that it is achieved. Let me denote it. Axis. Yes, and reversible adiabatic case would be such that the process is being achieved in a reversible adiabatic manner, okay, or an isentropic manner. So it will represent a straight vertical line in the TS plot. Now similarly, if instead of if the compression was achieved irreversibly, it will result in some point that is being diverted from the ideal case. So it's at some point 2, that is at a point higher than uh, the isentropic case, okay, and you will see why. Again, you can intuitively understand that if the work required for an ideal case is say h1 minus h2, then similarly in an irreversible case, of course it would imply that since there are some internal irreversibilities in the system, say because of friction in the shaft or the improper insulation of the compressor, then the net work required to achieve the same effect would be higher in the irreversible case compared to the reversible case. Okay, it's an intuitive understanding. So similarly, it will basically imply that now the actual work that is being required to pump the fluid is greater than the reversible work required in the case of ideal case. Okay, so we will have that. Now thus since W actual is higher among the two, then we can write eta isentropic for a compressor as W reversible by W actual, or H1 minus H2S by H1 minus H2. Okay, or if we consider an ideal gas, it will basically be T1 minus T2S, because there will be a Cp term here. It will cancel out in both from both the numerator and the denominator. We will have T1 minus T2S by T1 minus T2, or basically it is W reversible by W actual. Okay, the smaller over the bigger ratio. Okay, the ratio of the smaller over the bigger value. Okay. Similarly, in the case of a nozzle, we will consider again the first law. If we consider the first law, we will have d by dt plus is equal to q dot minus w dot plus m dot. If we consider a single inlet and single outlet, we will have m dot plus, and of course for a nozzle, like we consider these systems individually only, so we will have a single mass flow rate. So d by dt would be, and the mass flow rate, the mass conservation has to be there, so we consider a generic mass flow rate m dot. So we will have d by dt is equal to q dot minus w dot plus m dot hi plus vi square by 2 gzi minus m dot he plus ve square by gzi. Now if we consider a steady state, then this term will go out and d by dt will be equal to 0. Net work interaction is also 0, since it's not there is no work produced in the case of nozzle. Similarly, if we consider it to be insulated, then there is no heat interaction. Then again we can consider this the entire process that occurs through a nozzle as an isentropic process. So we will have that. Now if we simplify it a bit further, we will have that hi minus he is equal to ve square minus vi square by 2. Okay, if we consider it, the inlet and exit to be the same datum or same height level, then we will have this, the potential energy terms being cancelled out. Okay, so again the in the work, the net change in the enthalpy in the case of an isentropic case would be Cp T1 minus T2S, and in the actual case it will be Cp T1 minus T2. Okay, if we're considering an ideal gas. Okay, or in a more general fashion, you can write as in the case of isentropy it will be H1 minus H2S, or in the actual case it will be H1 minus H2, some point which is defined from 2S. Okay, and similarly the efficiency of the nozzle will be given by W isentropic, the isentropic value over the the actual value over the isentropic value. Okay, now and since in this case we do not have any comparison that whether the work, there's no entity to compare, like since there's no work interaction, there's only change in enthalpy. So
because in the case of the turbine and the compressors, there was an intuitive understanding that the work produced in the case of turbine would be less, the irreversible work produced in the case of turbine would be lesser than the reversible work produced in the turbine. So the actual work will go as a numerator and the reversible work will go in a denominator. Similarly, in the case of compressor, we knew that since the actual work required will be higher than the reversible work required, so the reversible work will go upon in the numerator and the actual work will go in the denominator. And here in the case of nozzle, since there is no such intuitive understanding or intuitive conclusion of which among the two would be higher, so we take the generic understanding that since the isentropic case is the most ideal case, in the case of nozzle only, then we expect that the net enthalpy change in the case of isentropic case would be higher than the net enthalpy change in the actual case because of the irreversibilities in the actual case. So that's why we'll have that eta nozzle would be equal to the actual change in enthalpy is H1 minus H2 over the isentropic change in enthalpy, this H1 minus H2s. And now from this equation, if we consider the inlet velocity to be much lesser than the exit velocity, then we can easily write eta nozzle as V square by VES square, okay, where this is the exit velocity in the case of an isentropic case. Okay, again, so here I will skip this part. So this is just a representation of the work achieved in the case of pump, and we can also compare, but this was not done in the class, so I am just skipping this part. But it is good, like let's go through it once, like just an analysis of the work done from a pump. So the work done from a pump can also be given by HI minus H, W is equal to HI minus HE, net change in the enthalpy. So from the TDS relations, we can write TDS is equal to DH minus VdP. For isentropic case, DS will be equal to 0, so we will be left with DH is equal to VdP. Or in the case of a pump, since it is a work consuming device, so the net work interaction would be equal to dW will be equal to minus VdP, right? If DH is equal to VdP, then since the work consuming device, so delta W will be equal to minus VdP. We are taking into consideration the sign convention, right? So W would be equal to minus net work will be equal to integral of this value, this is integral of minus VdP. V is the specific volume, and then W would be equal to, if we are considering V to be constant, then we can write W is equal to V integral of dP, because if we are considering pump and we are considering that is the working fluid that is being pumped is say liquid, then which is usually the case, then in that case the net change in the specific volume is usually very less, and we can ideally consider this specific volume to be constant. So basically, if we consider the fluid to be incompressible, then we can take the specific volume out of the integral. So we'll have W is equal to minus V minus V integral of dP. Integral of dP would basically give us minus V into P minus Pi. Okay, the net change in the pressure after pumping. Okay. So now let us look into some more derivations, some more detailed derivations of the principle of increase of entropy, and we'll be introduced with the entropy generation. Entropy generation is basically the net entropy generated because of irreversibilities in the system. Okay, so we know that ds is greater than equal to 0. The net change in the entropy of the universe is greater than equal to 0, or in general sense, ds is greater than equal to 0. It's equal to 0 only in the case of a reversible process, reversible adiabatic process. Okay, and we know that ds is greater than equal to delta q by t, and it's equal to delta q by t in the case of a reversible process. Okay, so in general we can write ds is equal to delta q by t plus delta s gen. Okay, or this is greater than equal to 0 because it will basically imply it is delta s is equal to delta q by t plus some term, right? So we can write this some term as delta s gen, that entropy generation because of the irreversibilities in the system. But we know that delta q reversible is equal to tds, right? And delta q irreversible would be something, since from this equation we can write tds as greater than equal to, let me just write it, it will have tds, from here we can write tds is greater than equal to delta q. Okay, right. So 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 now from here we know that from this equation we will have TdS is equal to delta Q plus delta S gen. Okay. Now if we take delta Q reversible as equal to TdS, then we will have delta Q reversible is equal to delta Q irreversible plus sorry yes, to be T delta S gen, right? So from here we can write delta Q irreversible as equal to delta Q reversible minus T ds gen, and since we know this is equal to TdS, we can write delta Q irreversible is equal to TdS. Might be confusing, so just TdS minus T. Sorry for this bad representation all the time, so it will be delta S. Okay. And again, some of you may ask that, sir, representing ds in the case of reversible case, and why you are representing delta S gen as some path function? Because the entropy generation is a path function. That's why we're representing the entropy generation as a delta rather than the complete differential d. Okay, so that's why you're using delta. So now so I hope this is clear, like how we arrived to this this part. So it's a simple equation that we're just using these equations. Okay, it's very simple. I hope this will make things more clear. Okay, so from the first law we have that delta Q is equal to du plus delta W. Okay, just kindly wait for 1 minute. I'm just looking to something. Just 1 minute. Okay. Kindly wait for 1 minute. Okay. So from the first law we know that delta Q is equal to du plus delta W. Okay. Now similarly, if we write the first law for an irreversible case, irreversible process, we'll have that delta Q irreversible is equal to du plus delta W irreversible. The important thing to know is that the first law is a conservation law, so it is valid for both reversible and irreversible processes. Okay, it does not, we are not at all introduced, at least in this generic form, we are not at all introduced with any concept of irreversibilities. Like we just say a generic statement that energy is conserved, so it doesn't matter whether it is achieved through a reversible or irreversible process, doesn't matter, so energy has to be conserved. Okay, so from the first law, if you consider a generic case, we can write as delta Q irreversible. For irreversible process, we can write as delta Q irreversible is equal to du plus delta W irreversible. Okay, now from a TdS relation, TdS equal to du plus PdV, you can write du as TdS minus PdV, right? So we substitute it here, so we can have delta Q irreversible is equal to TdS minus PdV plus delta W irreversible. Okay, and TdS minus PdV, let me go back, is equal to delta Q reversible minus delta W reversible, right? Because du is delta Q minus delta W, right? So since it is valid for du is a point function, so the change in the internal energy would remain same for both reversible and irreversible process. So we can write du as delta q reversible minus delta w reversible, which will also be equal to delta q irreversible minus delta w irreversible. Okay, so if we are considering two parts, the first is a reversible process, second is an irreversible process, and since energy, internal energy is a thermodynamic property or a point function, then change in the point function would not depend on the path, it will remain constant. So whether it is reversible or irreversible, it does not bother. So change in internal energy would be same, and if we apply the first law for both a reversible and irreversible process, we will get that du is equal to delta q reversible minus delta w reversible, and it's also equal to delta q irreversible minus delta w irreversible. Okay, so from that we can write that tds is minus pdv would be equal to delta q reversible minus delta w reversible, okay, and plus delta w irreversible, which is the same, the same term here. Okay, so here right now we are just going to finish the discussions by Professor Anand in the lectures. We are just about to finish the discussion, and then right away we will start the problem solving. We will start the problem solving part. Okay, so I hope that you are well versed with the discussions that were done in the lectures. So that will be important for solving the sessions, solving the questions in the today's session. So okay, so that's it. So okay, so let me continue. If you have any doubt in between, you can ask. Okay. Okay. So from this equation, we have that delta q irreversible. We are right now discussing about the entropy generation term. So I'm just discussing derivation done by Professor Anand in the lectures. Okay. Good evening. Good evening. So we are right now discussing about the entropy generation and its derivations. Basically, we're trying to understand the gist of entropy generation. What does it actually mean, and deriving some equations to understand that. Okay. So delta q irreversible will be equal to delta q reversible minus delta w reversible plus delta w irreversible. Now, if we arrange these equations accordingly, we will again get that delta q reversible minus delta q irreversible. We take this on the right hand side, would be equal to delta w irreversible minus delta w reversible, and this would be equal to tds t into ds gen. Okay, and how this comes into picture, because if you go back up from this term, from this equation, you can easily tell that delta q reversible minus delta q irreversible is equal to tds gen, and since this is equal to delta w reversible irreversible minus delta w reversible, we will get that delta w irreversible minus delta w reversible is also equal to tds gen. Okay, or we can conclusively write delta w irreversible is equal to delta w reversible minus tds gen. Okay, and here you can clearly see that the net work done by the system irreversibly is lesser than the work done by the system in the reversible case. Okay, so this is the equation that states that. Or from here also you can clearly see that the net heat transferred to the system, or you can write this one as, or you can consider this equation itself. So net heat transferred within the system irreversibly is lesser than the net heat transfer within the system in a compared to a reversible case. Okay, so this is something that gives you a mathematical proof to the intuitive understanding that we initially had while analyzing the different thermodynamic systems such as the compressors, turbines. So this gives you the intuitive understanding, like why the work done by the compressor is irreversible work done by the compressor is lesser than the work done by the compressor in the reversible case. Okay, sorry, why the work done by the steam turbine is, why the irreversible work done by the steam turbine is lesser than the reversible work done by the steam turbine, or why the work required by the steam turbine by the compressor is, why the irreversible work required by the compressor is greater than the reversible work required by the compressor. Okay, why this is the case? So this is the mathematical proof to that statement. Okay. if we go down, and this TDS gen, this term is known as the lost work. Okay, because you can clearly see that there is a reduction in the irreversible case when compared to the reversible one. So this TDS T into delta S gen term is known as the lost work. Okay. So now if we consider a Carnot cycle, say, which can be represented by as a as this as a square or a rectangle, like in the TDS plot. So let us consider that the lower temperature of heat interaction is T naught and the higher temperature is some generic temperature T, and here T naught represents the ambient temperature. Okay, so we are concerned in finding out what will be the highest possible amount of work that can be achieved by a Carnot cycle. So by intuitive understanding, we can from if you look into the formula for the efficiency, we will see that if T naught goes down, like if we have the higher source temperature as some constant, and if the T naught or the temperature of heat rejection goes down, then the efficiency would go up, right? So that's our intuitive understanding. And so what is the lowest possible temperature in the case of this Carnot engine? So the lowest possible temperature for the sink would basically be the ambient temperature, right? And some may again ask, like, why not a temperature lower than the ambient temperature? Why not the freezer? Because again, if you're achieving a temperature, if you're trying to achieve a temperature lower than ambient temperature, it basically means that you're again putting in some extra work. You're using an air conditioner or a freezer to reduce the temperature of the of the environment at where you're trying to establish the Carnot engine, right? And that very requiring that very scenario of achieving a cooler temperature than ambient require some additional work, which again, if we add up, would result in a decrease in the efficiency of the net cycle, right? So the lowest possible temperature in an ideal case would be the ambient temperature, right? So the highest possible efficiency of the Carnot cycle would be in the case where the sink temperature is equal to the ambient temperature. Okay, and that's why it represents the highest possible work that can be achieved from a Carnot cycle. Okay. Now, for a thermodynamic cycle, we know that cyclic integral of delta Q is equal to cyclic integral of delta W. Okay, which is basically the first law for a cyclic process. Now, when we look into this into this diagram, since this is a cyclic process, then we know that the TDS plot tells the area under the TDS diagram gives us the net heat transfer. Okay, or in the cycle it will basically be this red line. These red lines or area that is shaded by this red line, we denote the net heat produced by the Carnot cycle. And since this is a cyclic process, this will also be equal to the net work achieved by the Carnot cycle, because it's working in a cyclic process. So the net heat interaction is equal to net work interaction in the case of cyclic process, right? With that analogy, we can say that this blue dashed line would basically represent the net heat lost, or the net heat that was exchanged while during the operation of the cycle, right? Since we know that from the Kelvin-Planck statement that there has to be two thermal reservoirs for the operation of a heat engine, that's why this represents the net heat lost during the operation of the Carnot engine. Okay, and this area this blue dashed area within the TS diagram for the Carnot cycle basically represents the net unavailable energy. Okay, this is the limitation, this is the energy that we are losing during the operation of the cycle. But this is something that we cannot control, right? We do not have any control upon, because this is the temperature, this is the lowest possible temperature that we have in our hand, and if this temperature goes up, this unavailable energy will also go up. Okay, and that's why this is the unavailable energy that we just cannot ever achieve. This is the what to say, the this is the top, this is something that we can be said about, we cannot achieve. This is the energy that we can never achieve. This energy will always be discarded as a consequence of the second law of thermodynamics. Okay, basically by the Kelvin-Planck statement. And so the net available energy would be given by T minus T naught into delta S. Okay, T minus T naught into delta S. So I think that's all. And finally, let us. Is it clear about the concept of unavailable energy? Okay, thank you. And again, there's some another statement, that is a statement that Professor Anand uses, that is the extent of irreversibility, or I. So he represents it as I. The extent of irreversibility is represented as I, which is basically the difference between the net reversible work, the minus between the net reversible work and the net irreversible work. Okay, which is basically will be equal to T naught delta S gen. Okay. Again, Professor Anand also discussed the case where we are considering some different cycles, which is not a Carnot cycle. So if you are considering a heat interaction where the heat was taken from the source in a constant pressure process, say, in that case, since this is not a constant temperature line, this is not a constant temperature line, we cannot generically write the the available energy in this form. So in that case, the net unavailable energy would remain same, because the temperature of heat reaction would be the constant temperature of the ambient, right? So this will remain constant. So net unavailable energy will again be represented as T naught into delta S, but the available energy would ideally be represented as the net area under this curve, because the net area under this curve would be basically be given by T into ds, right? It's a generic form to find the area under the curve. So it is T into ds minus T naught into delta S. Okay, is the more general form, and if it is constant, then it will basically become T into delta S. So we can write T minus T naught into delta S. Okay. So finally, Professor Anand, let us derive the Bernoulli's equation from the steady flow energy equation. So let us look into it. So do you know about Bernoulli's equation? Like in the have you learned about it in the fluid mechanics, if you have taken the course? Just wanted to know, nothing. Yes, okay. So like then you will find it interesting. Like I think if you watched the lecture, you found it interesting, like how Professor Anand derives the Bernoulli's equation from the steady flow energy equation. Okay. So in that case, I don't think I need to derive it once again, but just I will go through it once for the viewers who will watch the video later on. So from the steady flow energy equation, if we consider a steady state, then if we consider a device which has no heat interaction or work interaction, then Q dot term will go up, and W dot will again be equal to 0, because there is no work interaction. And for a steady state, the net energy interaction would be d by dt would be equal to 0, right? So this device basically, since there is no heat and work interaction, can be considered as a flow duct. Okay, you can also consider it as a nozzle or a diffuser, but we are basically now consider a flow duct. Okay, duct, or basically flow through some channels. Okay, now the terms that we are left with are these two terms, right? So now if we rearrange it, then we will have that Vi square plus dzi equal to He minus Hi plus Ve square by 2 plus dz. Okay, these terms we have just rearranged. Okay, there is no nothing additional derivation required to do that. Now we want to manipulate this enthalpy term, and how we can do it? We can again take the help of the thermodynamic property relations, right? So we take the help of this equation, Tds is equal to dH minus Vdp, because this relation has the enthalpy term in it. So for an isentropic case, ds will be equal to 0. We will be left with dH is equal to Vdp. From that, since V represents the specific volume, which will be equal to the inverse of the density, so we can write dH is equal to 1 by rho into dP. Or for a constant density process, or for incompressible flow, we can write delta H is equal to 1 by rho into delta P. Now if we substitute this in this equation, we can easily write Vi square by 2 plus dz is equal to 1 by rho P minus Pi plus Ve square by 2 plus dze. Now if we again rearrange, like if we just take Pi by rho in the left hand side, we will be left with Pi by rho plus Vi square by 2 plus dz is equal to P by rho plus Ve square by 2. Yes, exactly, plus dz, which is the Bernoulli's equation. Yes. So this was done by Professor Anand just to show you the analogy, the thermodynamic analogy towards to the fluid dynamics, because in the case of mechanics of fluid dynamics, this is a very fundamental equation for understanding uh, energy conservation in fluid flows. So yeah, that's all from the discussion part for today's session. So now we will directly go to the problem solving part. So can you kindly wait for 1 minute? 1 minute. I will just I forgot to load the questions sheet in the for in this presentation. So I will just load it once, and I will then reshare the screen. Okay, is it fine? Okay, just kindly wait for 1 minute. Okay. Okay. So is the screen visible? Is the screen visible? Okay. So let us go to the first questions. So again, the first question is quite simple. This was discussed by Professor Anand in the lectures. So you can right away tell me the answer if you don't know the answers. That will be fine. And since I also discussed it, I won't go to the solution once again. So first question is, for an ideal gas on a TS plot at the same temperature, there are three statements. The constant volume curves have higher slopes than constant pressure. Both constant pressure curves and constant volume curves have the same slope, or both okay, I'm sorry. This is wrong. So this should be the opposite. The constant pressure curves have higher slope than constant volume. So yes, so which is correct? Can you tell? This was discussed by Professor Anand. He derived it in the lectures. So can you tell the answer? if you have written the notes, you can just even go back to your notes and tell me the answer. A. Okay, that's correct. So since this was discussed by Professor Anand in the lectures, and even I discussed it in today's session, so I don't think I will have to revisit the derivation once again. So this is correct. Okay. So let's directly go to the next question. A heat source at 100 Kelvin loses 2000 kilojoules of heat to a sink. Okay. The sink temperature is at 300 Kelvin, and in the case 2 the sink temperature is at 700 Kelvin. Okay. So the which heat transfer process is more irreversible, case 1 or case 2, or is it the same in both the case? Okay. So you can either derive it entirely, find the net entropy change, or you can just tell me on the basis of your intuitive understanding. Like I think Professor Anand discussed about it when in the week before previous week session, like about the irreversibilities that can be generated because of a temperature change. So you can do that, or either you can just simply find the net entropy change, like you can do something like Q source B. Okay, so let me look into it for the viewers as well. Plus Q sink. Can you tell why, or is there any numerical value for supporting your answer? Either the statement is also fine. Like, of course, there is a statement for this. 700 is near to 100. Yeah, exactly. So there are two ways to solve this answer. First, yes. So case 2 is oh B. So you are saying case 2 is more irreversible, right? Is it so? Oh, case 2 is more reversible. Okay, now that's correct. So you are saying case answer is A, right? Correct? Okay. So yeah, that's the case. I guess Professor Anand time and time again discussed or stated this in the lectures that as the heat difference or sorry, as the temperature difference during the heat transfer increases, the irreversibility during this heat transfer process also increases. Okay, so an ideal heat transfer process, or an least or a heat transfer process with the least amount of irreversibility would be a process that has least temperature difference during the heat transfer, which is actually impossible to achieve, and that's why achieving heat transfer in a reversible manner is extremely difficult to achieve. For that, you need to almost yes, the difference in the heat temperature should be very small to achieve a reversible heat transfer. But since it is not possible, because by the very process, the very directionality of heat transfer is determined by the degree of temperature difference. So that's why this is very hard to achieve. Okay, that's why we say that isothermal heat transfer is very hard to achieve. But and that's why in that line of thought, we can, by looking at the temperature between the source and the sink, you can directly tell that since in case 2 the temperature difference between the source and the sink is lesser than the temperature difference between the source and the sink in the case 1, that's why case 1 should be more irreversible. Okay, and similarly, like if you are also going through a mathematical means of yes, okay, I'm just showing the answer so that the other viewers can revisit and just look into compare the solution. So if you are going to compare it, we are going to take a mathematical way to prove it, you can also do that. So in the case 1, since source heat transfer to the source is 2000 and temperature over the source is 1000 Kelvin, and in the case of sink, again the net heat transfer to the sink was same as literally 2000. So you can consider, rather than considering it as a heat engine, you can consider it something like interface, and this is the source, and say it is the sink, and 2000 joules of heat is being transferred from the source to the sink, and this source and sink are at different temperatures. Okay, you can consider something like that. Okay, rather than consider heat engines that need to have, say, difference in the heat transfer, you can consider it as an interface where the heat is being transferred from the source to the sink. Okay, if you with that understanding, if you substitute the value of the Q source, Q sink, and T sink, you will get that for case 1 you will get the net change in the entropy as 4.667 kilojoule per Kelvin. And in the second case, if you substitute the value of all this, you will get that the net change in the entropy is 0.87 kilojoule per Kelvin. So you can clearly see when the temperature difference between the source and the sink is less, the net entropy change is also less. Okay, or you can clearly say that case 1 is more irreversible compared to case 2. Okay, so let us look into the next question. Choose the correct statements. Okay, A, increase in the entropy principle implies that the entropy of any system cannot decrease. Or entropy change of a system can be negative during a process. Entropy is never conserved. The entropy generation of a system can be negative during a process. So which among the of these 4 statements is correct? Or are there multiple correct statements that can also be there? So you can tell me the answer. B and C. Okay, so actually, like okay, so the correct answer is actually B. So yeah, why? Because entropy of the system can be negative, as we clearly saw in the previous solution. Like in this case, if we consider the entropy change for the source, it is some negative value, right? It will be -2, right? This is -2 for the case of the source, right? So entropy change can be negative for a system. And secondly, entropy is never conserved. Okay, so in general sense, if we think, this is correct, because in general we can never it's very hard to achieve reversible heat transfer. So entropy conservation is very difficult. But if we consider a reversible heat transfer, so we can, in that case, we can clearly write the entropy change as being equal to that reversible heat transfer over the temperature at which the heat was transferred. So in this case, we can say that the entropy is conserved. Okay, but is it correct? Is it fine? Yes. Okay, so in a reversible case, you can say entropy is conserved, but in general sense, intuitive understanding tells us that since it's very difficult to achieve such kind of heat transfers, reversible heat transfers, so we can, in general sense, most of the time the entropy is not conserved because of the entropy generation term. Okay, so question number 4. Okay, so I think I can skip this. I can go to it if required in the last part of the discussion, but let us go to question number 5. Okay, a heat engine receives heat from a source at 1200 Kelvin at a rate of 1200 kilojoule per second and rejects the waste heat to the sink at 400 Kelvin. Okay, if the power output of the engine is 400 kilowatt, the second law efficiency of this heat engine is question mark. Okay, so the second law efficiency, let me just give you the formula. The second law efficiency would be the actual efficiency. Let me write it as eta actual by eta ideal. Okay, and eta ideal or ideal efficiency would be the efficiency of a Carnot cycle. Okay, if instead of this heat engine, if we substitute this heat engine by Carnot engine, the efficiency of that Carnot engine would be taken as the ideal efficiency. Okay, think it's quite simple. Just substitute the values. You need to find the actual efficiency first, and then tell me the answer. 0.5. Okay, so the answer is correct. But just for the purpose of purpose for the help of other viewers who would watch the video for comparing their solutions, let me just go back to the derivation. So again, the second efficiency is given by efficiency of the actual cycle by the efficiency of the ideal cycle. Okay. Yeah, exactly. So here we can take the net work done. The efficiency of any heat engine will be given by the net work done by the net heat input. Okay, so it will be W by QH over 1 minus TL by TH, which is the efficiency of a Carnot engine operating between the same temperature difference or the same temperature of the source in the sink. Okay, so net work output is 400. It was 400 watt, and the net heat input was 1200 kilojoule per second or 1200 watt. Okay, and the efficiency was for the Carnot efficiency, the temperature of the sink was 400 Kelvin and the temperature of source was 1200 Kelvin. Let me just verify it one. Okay, yes, it was 400 Kelvin and 200 Kelvin. So if we substitute these values, then you can easily calculate it to find that the second efficiency is 0.5 or 50%. Okay. Now let us look into some interesting question. Okay, the last, I think these two questions are quite interesting. So I have to do something. I think question number 6 is completely visible now. Okay, let us go through it. Okay. A quantity of air undergoes a thermodynamic cycle consisting of 3 processes. Process 1 to 2 is a constant volume process. Constant volume heating from P1 equals 0.1 megapascal to T1 equal to 15 degrees Celsius and V1 equal to 0.02 meter cube to P2 is equal to 0.42 megapascal. Process 2 to 3 is a constant pressure cooling. Okay, it's a constant pressure cooling. And process 3 to 1 is an isothermal heating to the initial state. Okay, employing the ideal gas model, so you can consider the working fluid to be ideal gas. And Cp, you need to take Cp as 1 kilojoule per kg Kelvin. Evaluate the change in the entropy of each process. Okay, so you need to find delta S 1 to 2, delta S 2 to 3, and sorry, it would be S2 minus S1, S3 minus S2, and S1 minus S3. Okay. I will give you a clue. Clue would be to use thermodynamic property relations. Okay. And they are basically TDS is equal to du plus PdV, and TDS is equal to dH minus VdP. Okay, so if we draw it in a PV diagram, so process 1 to 2 is a constant volume heating. Okay, constant volume heating, so the fluid will expand. Then 1 to 2, 2 to 3 is a constant pressure cooling. So sorry, constant volume heating, pressure will go up. Constant pressure cooling, volume will go down, and it's a isothermal process to reach point 1 back again. Okay, so this is the diagram in the PV diagram for the cycle. Okay, so you can integrate these equations. You can integrate these equations to find the net entropy change for these different cycles. Okay, so first task would be, I guess, to find T2. Okay, so let us let me give you 5 minutes to look into the solution, and then you can show the solution, compare our solutions. Okay. Okay, okay, sure, sure. You can take more time. That's completely fine. First thing is that you can, since process 1 to 2 is a constant volume process, you can use the ideal gas law to find the temperature T2, because pressure 2 is already given. Then you can proceed with that. So could you find T2? Can you tell the value of T2? Because you will. Yes, 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 exactly. Perfect. Then from that, if you use the TDS relation, you can easily find the value of S2 minus S1. because since this is a constant volume process, so the second term will go up. Sorry, it will second term will be removed. Okay. So oh, okay, and then you can one more thing to catch is that since you are seeing that Cp is the is given in terms of 1 kilojoule per kg Kelvin, so you need to also find the mass of the fluid in the net quantity of fluid in the process, mass of the fluid. So you need to find m. So m again can be found from the ideal gas law. So m would be something like P1 V1 by RT1. Okay. So P1 is 0.1. So just keep it in terms of kilopascal. So it is 100 kilopascal. V1 is 0.02. R is 0.287. Okay, something I didn't give, but it is the specific gas constant for air is 0.287 kilojoule per kg Kelvin, and T1 would be is 15, so it is 288 Kelvin, right? So can you tell that what is m? Yes, it is 0.024, and T2 is 1209. Okay, so it is something, ideally it should be some R ln, sorry, oh no need of m because volume is already taken in the mass. Yes, so yes, exactly. So second term will go down because it's a constant volume process. So we will get 0.034 kilojoule per kg Kelvin. 0.034. Let me check the units. Yes. Is it joules or kilojoule per? Oh, there actually there would be an m. Okay, so this 0.034. Okay, is it? Let me just check it. So m is 0.024 into CV. Okay, CV would be Cp minus R, right? So Cp is 1 minus 0.287 into ln 1209 by 288. Okay, so let me check. Yes, Cp is 1 kilojoule per kg K only, right? Yes, but you need to find Cv, right? Because it is Cv, right? For constant pressure process, this is du, so mCv into ln into T2 by T1. Okay. Let me just check. I don't know the answer. So it comes around 0.0246. Can you just verify? Yes. Okay. Then you can find the next one. It is constant pressure cooling. Okay. So what do you have? You have P2. Here you know P2, so P2 equal to P3, right? That's you have. So you can write this as mCp ln T3 by T2, right? Now the interesting thing is that since from this statement that isothermal heating to initial state, so since it is isothermal, it will basically mean that T1 is equal to T3, right? So you will have T1 equal to T3, and since you know T3 now, T2 is already known, you can easily find this one, right? And the second term will go out because it will be something like mR ln P3 by P2. This will be again equal to 0 because P3 is equal to P2, right? Quite simple. You already know T3 because they are saying that it is isothermal heating to the initial state. So T1 will be equal to T3, right? So now you can easily find this mCp ln T3 by T2. So can you tell the answer? So S3 minus S2 would be 0.024 into Cp is 1 into ln T3 is 288, T2 is 1209. So can you tell the answer? Correct, exactly. So you can here clearly see that now the entropy of the, yes, the entropy of the process has gone down, right? So there are obviously there are some instances where the entropy can be negative, but the net change of the entropy, the summation of the net change in the entropy of the system and the surrounding has to be positive. Okay, so that's the principle of increase of entropy. Okay, so the last is S1 minus S3 is isothermal change in the isothermal heating to initial state, right? So now it would be, again you can consider either of them. So let us consider the first one. It will be, what do we have? I guess we have all the terms, so we can use either of them, right? Either of them. So let me write it somewhere here. Okay, so S1 minus S3 should be M, say I am using the second one, Cp ln T1 by T3 minus Mr ln P3, sorry, P1 by P3. Okay. We have, because we do not know V3, but we know P3. How? Because process 2 to 3 is a constant pressure cooling, right? So P2 would be equal to P3, right? And since it is isothermal cooling, this term will go down, so we will be left with S1 minus S3 is equal to minus Mr ln P1 by P3. So P1 you already know, it is given. P3 is equal to P2. P2 is also known, so you can substitute the values and tell me the answer. Minus 0.59. Can you please check? Let me verify. Okay, I'm not sure. It may be correct, so let us check. Okay. So let me write it here somewhere. S1 minus S3 would be, M is minus 0.024, R is 0.287, natural log of P1, if I go here, P1 is 0.1 and P2 is 0.42. Yeah, 0.44, you are saying 0.44. Okay, let me check. Let us calculate it. 24 into 0.287 into natural log of 0.1 by 0.42. So it turns out to be 9.88 into 10 to the power minus 3 kilojoule per Kelvin. So is it okay? This should be ideally the answer. So is it okay? Can you check your calculations? Have you done the same? Have you substituted the same values for? So I want left question answer. I didn't get that. Can you please say that? Which one? Can you tell? I'm not understanding. You mean question number 7? I am not getting your last statement. Can you please repeat? Explanatory type questions. So can you tell the question number? Are you telling from the assignment? Like I'm not getting clearly, so you can. Yes. So question number, because I cannot, like as per the regulations, I cannot tell you the answer directly. So maybe if I look into the question, I can help you out with some clarification, but I don't think I will be able to tell the answer. But let us see what your question. Can you tell the question number? Not appear in the screen. Okay. I don't have any explanatory type questions in the question, this question. So question number, is it the match the following, this one? Are you telling about this one? Question number 4. Oh, you want the derivation for this answer? Question number 4, right? Is it? Okay. So question number 4 actually, sorry, not this. Which one then? I think, see, there may be some questions similar to the questions that are in the assignment, but they are not the. But all of them are not the same. Okay. I think I only take usually one or two, so that you can get an idea of solving the assignments. And most of the questions are something that I take from different textbooks or reference books. Okay. So that's why it may not be the same. So okay, so if you have any doubt, you can just put in the discussion forum. I will try to reach out and solve the question, discuss about it. But let us look at the final question. Okay, I think we are going out of time. So this final question, it's a bit tricky one, but it's interesting. And for the sake of saving time, I will directly go to the solution. You can go to the look into the solution with me, along with me, and just tell me if you have any doubt in the solution, you can ask me. Okay. But for the sake of saving time, because the time is going to be finished soon, so I am going to directly go to the solution. Okay. So let's go to the question first. Question number 7. A system has a heat capacity at constant volume Cv is equal to AT square, where A is equal to 0.042 joule per Kelvin cube. Okay. So they have given the value of A and the units are joule per Kelvin cube. So T square will have a unit of K square. So K square into A by K cube, sorry, K square into joule by K cube would give a unit of joule per Kelvin. So the Cv is in terms of joule per Kelvin. Okay. The system is originally at 200 Kelvin and a thermal reservoir is at 100 Kelvin. Okay. What is the maximum amount of work that can be recovered as the system is cooled down to the temperature of the reservoir? Okay. So now I hope the question is clear. Is the question clear? A yes or no would be fine. Then I can directly go to the solution. Is the question clear? They're just saying that there is a heat source at 200 Kelvin and a heat sink at 100 Kelvin, and they have given the value of the specific heat capacity at specific volume. Okay. Okay. So not heat capacity, specific heat at constant volume. Okay. So they've given the value of Cv. So now they're asking what is the maximum possible amount of work that can be achieved for a cycle that operates between 200 Kelvin and 100 Kelvin. Okay. So let us go to the solution. Okay, so this is the schematic diagram of our problem. So the T1 is the source temperature at 200 Kelvin, T2 is the sink temperature or reservoir temperature at 100 Kelvin, and we are generating the heat engine that operates between the two reservoirs generates a work W, and it absorbs the heat Q1 from the source and rejects the heat Q1 minus W from the reservoir, because for a cyclic process we know that Q1 plus Q2 is equal to Q1 minus Q2 is equal to W, so Q2 would be Q1 minus W. That's why I have written Q1 minus W. Okay. So now heat removed. Okay, so the heat removed from the system Q1 would be the integral from of Cv into dt from T1 to T2. Okay, so it would be, since it's a constant volume, can take it as constant volume heat exchange. So it would be Q1 will be equal to Cv into dt from integral from T1 to T2. Okay, and we know that Cv is equal to AT square as given in the question. So it will be integration from of AT square dt from T1 to T2. Now A is 0.042. We substitute the value of A here. Now integration of 0.042 t square dt from T1 to T2 would be 0.042 t cube by t, because integral of t square dt would be equal to t cube by 3, right? So 0.042 into t cube by 3 from 200 to 100, because now heat is being transferred from the source to the reservoir. Okay, so the initial temperature is T1 and it's transferred to a final temperature of 100, right? T2. So it will integration will be from 200 to 100. Okay, that's the catch in this question. So Q1 would be 0.042 100 cube minus 200 cube by 3, which you will find out to be equal to 98 kilojoule. Okay, it looks like Q, so I'm sorry, it is actually 98. Okay, 98 kilojoule. Okay, now for the system, the net entropy change for the system would be integral from T1 to T2 Cv into dt by t. Since it's a constant, we're considering it as a constant volume process. Okay, so you will have 0.042 t square dt by t from T1 to T2. Integral of 0.042 t square dt by t from T1 to T2. Okay, we're just substituting the value of Cv in this expression. Okay, sorry, Cv is equal to AT square or equal to 0.042 into t square. Okay, so you get that. Now if you integrate it, you will get, since t square, this t will get cancelled out, so the integration of t into dt will give you t square by 2. Okay, so we'll get delta S of the system is 0.042 t square by 2, integration from 200 to 100. So if you substitute the value, we will get delta S system as minus 630 joule per Kelvin. Okay, this is entropy change for the system. Now for the reservoir, since the reservoir, if I go back to the diagram, the reservoir absorbs the heat of Q1 minus W that is rejected from the heat engine. Okay, so the heat absorbed by the reservoir will be Q1 minus W. Okay, so delta S reservoir would be Q1 minus W, which would be 98,000 minus W, because it is 98 kilojoules. So it is basically Q1 is 98,000 joules minus the net work W divided by 100, which is the temperature of the reservoir. Okay, it's 100 Kelvin. And delta S of the working fluid in the heat engine would be 0. Why? Because it operates in a cyclic manner. The cyclic integral of the thermodynamic property, which is entropy, would be 0. So net entropy change of the universe would be the entropy change of the system and the entropy change of the surrounding. Okay, our surrounding in this case would be the entropy change of the reservoir. Okay, so and if I go back here, I'm sorry, I'm scrolling up too much. So the system would be this source at 200 Kelvin, and the surrounding or reservoir would be, surrounding would be this heat engine, and the reservoir, it is at 100 Kelvin. But since the entropy change of this cyclic heat engine would be 0, so the only entropy that we should be concerned with for the surrounding case is the entropy change for the reservoir at 100 Kelvin. Okay, I hope this is clear. Okay, so yes, so delta S universe would be delta S system plus delta S surrounding. So delta S system was minus 630 plus the delta S surrounding was 98,000 minus W by 100. And we know that from the principle of increase of entropy, we get that delta S universe to be greater than equal to 0. Okay, so that would imply minus 630 plus 98,000 minus W by 100 is greater than equal to 0. Okay, so if you divide this term by 100, you will get 980 minus W by 100 minus 630 is greater than equal to 0. Okay, or if we take this in the right hand side, you will be left with, if we subtract 630 from 980, we will get W by 100 is less than equal to 350, or W is less than equal to 35,000 joule, or the highest possible work that can be achieved from this thermodynamic cycle is 35 kilojoules. Okay, So here we make use of the principle of increase of entropy to find the highest possible of work that can be achieved by the heat engine. Okay. So that's all from my side. Yes, I hope this was clear. Again, if you have any doubt, you can go back to the recordings so that you can clarify and watch each and every step by pausing the video. But since we are out of time for today, so I have to stop the session here. So thank you thank you for attending the session and making it quite interactive one. And that's all for today from my side. Let's meet next week. Okay. Thank you.